Hello guys, the econometrician here, and this is basically a follow-up on my videos regarding the maximum likelihood estimator. And I've shown you guys how to derive the likelihood function, what the likelihood function actually means, and I've shown you guys how to estimate only a single parameter based on a certain sample. So today I'm going to show you guys how to actually derive an estimate for multiple parameters, and I'm going to do that using the normal distribution. So I'm just going to assume you've watched my earlier videos, so I will just go ahead and just start by the first step, which will be deriving the likelihood function. And the likelihood function in this case depends on two parameters, so we will write the likelihood function like this. But please remember, of course, the definition of the likelihood function doesn't change. That will still be equal to the product from I equals 1 till n of the probability density function of the xi's. And we will just write this out from I equals 1 till n from the PDF. And this video, guys, it will just be a lot of writing. It's not actually that hard, but it's just a lot of writing. And if we just simplify this further, we can see this does not depend on x, so we can just get it out of the product. So 1 divided by square root of 2 times pi times sigma squared raised to the power n, and times the product from I equals 1 till n of e raised to the power minus 1 divided by 2 sigma squared times x minus mu squared. And I forgot a bracket right here. And here, of course, you guys probably know that if we have like let's say we have e raised to the power x1 minus mu, and we do this times e raised to the power x2 minus mu, then this will just be equal to 1 to e raised to the power from the sum from I equals 1 till 2 from xi minus mu. So that's exactly what we're going to use right here. So that will give us that this is equal to 1 divided by the square root from 2 pi times sigma squared raised to the power n times e raised to the power minus 1 divided by sigma squared, because this does not at all depend on xi, times the sum from xi minus mu squared. Okay, so now we have derived this. I will once again tell you what this likelihood function actually means. This likelihood function basically tells us what is the likelihood of generating this data set right here for given values of these parameters. And of course we want to maximize the likelihood of generating such a data set. So we want to find the values of mu and sigma squared that maximize that likelihood. So we want to maximize the likelihood function as explained in step 2 as well. So let's get to step 2, and as you guys can see, the function is just differentiable, so we will find the maximum by just differentiating. And of course it will be way easier to differentiate the log likelihood, and if I've explained to you guys as well in my previous video why we can do this. So this will be equal to the log of, I will just write it out again, this whole expression right here. And of course I assume you guys know the rules for the natural log. Raised to the power minus 2 squared times the sum from I equals 1 till n of xi minus mu squared. Okay, so of course we can get n out of here. This will give us n natural log of 1 divided by 2 pi raised to the power minus a half. And of course here e just falls away because ln e raised to the power a, ln e raised to the power a is just a, so we're going to use that here, and this will just be equal to minus 1 divided by 2 sigma squared times the sum from I equals 1 till n of xi minus mu squared. Okay, so now we can split this further, because this will give us just minus n divided by 2 times the natural log of 2 pi sigma squared, and this will be minus 1 divided by sigma squared times the sum from I equals 1 till n from xi minus mu squared. Now, as you guys can see, we will want to separate this, so we can easily do this because we have the natural log. So this will give us minus n divided by 2 of the natural log from 2 pi minus, because of course this in brackets, minus n divided by 2 times the natural log of sigma squared minus 1 divided by 2 sigma squared times the sum from I equals 1 till n of xi minus mu. And guys, really it's not that hard what we're actually doing, it's just a lot of writing. Okay guys, so now we have derived the log likelihood function. I see I made a little mistake here. This of course need to be mu sigma squared. And now we have derived this, we will need to find the values of mu and sigma squared that will maximize this log likelihood function right here. And we will need to do them individually. So let's start with mu. Sorry for this ugly mu. And we will need to find the value of mu that will maximize this log likelihood function. And we will do this in the same way as always. We will just take the partial derivative with respect to mu from the log likelihood function. And as you guys can see from the equation above, this term does not depend on mu and this term does not depend on mu. So if we differentiate with respect to mu, of course this will be 0. So we will only be left with this term, and this will give us this, and then we will just take this term right here in front because it is also not dependent on mu. And then we will just write out these brackets right here, and that will give us xi squared minus 2 xi times mu, and of course this will be a plus mu squared. And now we can easily take the first derivative with respect to mu, so this will still be equal to this, and of course xi raised to the second power will just be 0, so that term falls away, and this will be equal to minus 2x. So let's write this out, minus 2xi, and of course this will be equal to plus 2 mu. Okay, so now as you guys can see, we can get this 2 out of the bracket right here, so that will give us divided by 2 sigma squared times 2, and we will also get this minus out of the bracket, so this will give us times minus 2, and then we will be left with this term right here, minus mu. Okay, so this will be equal to 1 divided by sigma squared times the sum from I equals 1 till n from xi, and we will actually separate these terms right here as well, minus 1 divided by sigma squared times the sum from I equals 1 till n of mu. And of course, before we set this equal to 0, we will need to check for the second order condition. So let's go ahead and do that right here real quick. So we will need to calculate the partial derivative of mu the second partial derivative with respect to mu of the log likelihood function, and this will just be equal to another derivative of what we have just found. And what we just found was 1 divided by sigma squared times the sum from I equals 1 till n from xi minus 1 divided by sigma squared times the sum from I equals 1 till n of mu. And this term of course will be 0, and of course we can get this in front right here, and then of course this will just be the sum from I equals 1 till n of 1, which of course will just be equal to minus 1 divided by sigma squared, and of course this 1 of course here will just be 1 times n, so of course this will be equal to 1 minus 1 divided by sigma squared, and this will be lower than 0 for every value of sigma squared and every value of mu. So now we have checked for the second order condition. We can go ahead and go back to this right here and set this equal to 0 to find the value of mu that will actually maximize the log likelihood function. So now we have set it equal to 0. We can multiply both sides by sigma squared, so that will fall away, and then of course we can just get the x's to the other side, so this will give us is equal to the sum from I equals 1 till n of xi, and of course just like of course this mu we can get it in front of the summation. So sorry guys, just a few more steps right here. I know I can do this a lot quicker, you guys probably as well, so sorry, but just to be clear, and this will give us n mu times n equals the sum from I equals 1 till n of xi, and this will finally give us that our maximum likelihood estimator of mu will be equal to 1 divided by n times the sum from I equals 1 till n of xi, which of course is just equal to our sample mean. So there you have it guys for the first part. We have now calculated the maximum likelihood estimator for mu. So I will just erase this right here quick, and then I will go ahead and go on with estimating our maximum likelihood estimator for sigma squared. So be right back. Okay guys, so now we have found the value of mu that will maximize our likelihood function. We will find the value of sigma squared that will maximize our likelihood function, and it will just be the same steps, only this is a bit more tricky. This term does not depend on sigma squared, so we will just that will just be 0. The second term does, so that will be equal to this. And please note that we do not have to do anything with the chain rule here, because we are taking the partial derivative with respect to sigma squared and not sigma, and that is what will make this second term a bit tricky as well. So I will just write it like this, and I don't need to forget the half here, and then we will need to take the partial derivative with respect to sigma squared of 1 divided by sigma squared, and this will be equal to minus n divided by 2 sigma squared minus a half times the sum from I equals 1 from xi minus mu squared, and this term right here guys, it will be equal to minus 1 divided by sigma squared, and that squared as well. So that of course will just be equal to minus 1 divided by sigma raised to the power 4. So let's go ahead and write that out right here. Sorry, I'm not being a bit neat. Okay, times the sum from I equals 1 till n of xi minus mu squared. So let's go ahead and simplify this a bit further, and we can do so by multiplying this bracket by sigma squared top and bottom. So we can actually put this right here in just one fraction, and I see I made a little mistake. This minus here cancels out with this minus, so this will be a plus. This will give us plus times the sum from I equals 1 to n of xi minus mu raised to the second power. And now we will go ahead, and we can't set it equal to 0 yet because we need to check the second order condition, so we will go ahead and calculate that right now. And we will need to take the partial derivative with respect to sigma squared of our likelihood function, and that will be equal to the partial derivative of the partial derivative function with respect to sigma squared we have already calculated. And I will be using this equation right here, so it will just be a bit easier to calculate. And this will equal, and I'm gonna make a quick substitution right here. I will say, okay, let theta equal sigma squared. It will just make it a bit more easier. Times minus 1 times sigma plus 1 divided by, theta plus 1 divided by 2 theta squared times the sum from I equals 1 till n of xi minus mu squared. And of course this will just equal minus n divided by 2 theta squared times minus 1 for the chain rule, plus 1 divided by 2 theta raised to the third power times minus 2 times the sum from I equals 1 till n from xi minus mu squared. And this of course will be equal to, the minus will cancel out, so this will be equal to n divided by 2 theta squared. And of course this minus here will get in front, so minus 1 divided by, and this 2 will cancel out with this 2, so this will be equal to 1 divided by theta raised to the third power times the sum from I equals 1 till n of xi minus mu squared. And now we will simplify this further by multiplying this bracket with theta, and then on the other side we will need to do times 2, so minus 2 times the sum from I equals 1 till n from xi minus mu squared. Sorry guys if I make these little mistakes, it's just a lot of calculations. And as you can see now, we can't really simplify this any further and say that it will be smaller than 0. So what you actually need to do in this case is we are going back to the first derivative, and we're actually going to calculate the value of sigma that will maximize the likelihood function. And then after that we're going to plug it in this equation and see if we get a value that's smaller than 0. So let's go ahead and do that right now. Let's say this equals 0, then of course both sides will be multiplied by 2 times sigma raised to the fourth power. So this will just be equal to this. And this will be equal to 0, and this will give us that sigma squared will equal, and of course now we're estimating, this to the other side will be minus, and then it will cancel out with this minus, so this will be equal to I equals 1 till n from xi minus mu squared divided by n. And please note that of course this we don't know this value of mu, so this is also equal, we replace the mu by the estimate of mu, and of course we can also replace this just by what our estimate of mu is, which is the sample mean. So this will be our estimator for sigma squared, but we still need to check the second order condition, and we have said that theta equals sigma squared, so we will plug in this right here for theta. So if we just do that right here, that will give us, and I'm just going to do it for only this part, is 1 divided by n times the sum from I equals 1 till n from xi minus x minus the sample mean, and I will just let this be mu, so it will be easier. And then I just rewrite the rest of the equation. And we could also substitute in the value of theta, mainly this, to the third power here beneath, but we already know that this will always be a positive number, so we don't need to plug it in really. This will give us this, and then if we simplify this further, you can see that these n's will cancel out, so this will give us the sum from I equals 1 till n from xi minus mu squared minus 2 times the sum from I equals 1 till n from xi minus mu squared divided by 2 theta raised to the third power. And we know, please notice guys, that this number right here is always bigger than 0, because this is a positive number, this is bigger than 0, so it's raised to the third power, and times 2 is also a positive number. And this will give us that this is equal to minus, oh, I forgot this 2 here, sorry guys, it's just a lot of writing and sometimes you forget something. From I equals 1 till n from divided by 2 theta raised to the third power. And of course this is a positive number and this is a positive number, so minus a positive number will of course always be smaller than 0. So there you have it guys, we've checked the second order condition, and this gives us guys that the maximum likelihood estimator for sigma squared is equal to this equation right here, and the maximum likelihood estimator for mu will be equal to the sample mean. So these are the results guys. I hope you guys enjoyed the video, and have a nice day guys.